Hello, and welcome to our discussion of eigenvalues. Let's review some finite dimensional theory with matrices. If A in Cn by n is a matrix, I'll use the notion Cn by n to denote the n by n complex entryed matrices. A point lambda in C is an eigenvalue of this matrix A if there is a non-zero vector x in Cn such that A times x equals lambda times x. And we always want the vector x to be non-zero because otherwise we'd have the trivial and useless situation of every point in the complex plane being an eigenvalue. Because, of course, a times 0 is equal to 0, and lambda times 0 is equal to 0, where here 0 is the 0 vector in Cn. Now, how can we generalize this notion to arbitrary linear operators that we can't necessarily write as n by n matrices? One thought would be to say that if we have vector spaces x and y, which as usual we'll take to be vector spaces over the complex numbers, and t is a linear operator from x to y, then a point lambda in C is an eigenvalue of t if there is a non-zero vector f in x such that t on f is equal to lambda times f. That pretty much seems to generalize our definition of eigenvalue from the finite dimensional case. There's one thing we might want to think a little bit about here in this definition. I have my operator t going from the vector space x to the vector space y, and I have this relation tf equals lambda f. So tf has to be a vector in y, because f was an x, and t maps x into y. So then lambda f equals tf also has to belong to y. Now say I'm in the case of lambda being non-zero. Then I can rewrite f as lambda times f divided by lambda. So lambda f is in y, and if I multiply that vector lambda f by the scalar 1 over lambda, I get lambda f divided by lambda is also in y. But that means f is in y. And I already had f in x. This is kind of weird. It seems that whenever f is an eigenvector of t, I would want f to be in x and y at the same time. So it seems like for this to make sense, I'm going to need x to be a subspace of y. Okay, we can live with that. Let's use a bit of different phrasing and notation. We'll say that a linear operator in a vector space x is a linear operator t from some subspace d of t into x, where here the space d of t is contained already in x. So what does this mean? T starts out on the vector space d of t. It maps this vector space d of t into x, and I'm assuming from the beginning that d of t itself is a subspace of x. Maybe d of t equals all of x, maybe not. So I'll pronounce this d of t or domain of t going forward. And here we have now our better definition of eigenvalue. If t from d of t into x is a linear operator in the vector space x, then a point lambda in C is an eigenvalue of t if there exists a non-zero vector f in d of t such that tf equals lambda f. So we have our good old eigenvalue relation, tf equals lambda f, and we've set up the domain a little better. We call f, of course, an eigenvector of t corresponding to lambda. And sometimes we'll call the ordered pair lambda f, where lambda is a complex number and f is a vector, an eigenpair of t. And since t maps d of t into x, I have t on f is a vector in x, and lambda times f is still a vector in d of t, but d of t is contained in x, so both tf and lambda f are in x, they live in the same space, everybody's happy. We can see this at the level of matrices, our familiar example in new language. Say we take x to be the vector space Cn, and we'll identify matrices A and Cn by n with linear operators on Cn by the usual matrix vector multiplication. So how does this operator act? It sends a vector x to the matrix vector product A times x. Then for any matrix A in Cn by n, we can certainly take its domain d of A to be all of Cn, because I can always multiply an n by n matrix with any vector in Cn. And then the eigenvalues of A are precisely the roots of the nth degree polynomial determinant of lambda times In minus A equals 0, where here In is the n by n identity matrix. In particular, this linear operator given by matrix vector multiplication always has eigenvalues in the complex plane. Here is a particularly uncomfortable example. A linear operator can have no eigenvalues. Of course, we'll have to go to some sort of infinite dimensional vector space, since otherwise we could identify it with a matrix. Let's take x to be the continuous functions on the interval 0 to 1, and we'll define tf as the operator given by tf on x equals x times f of x, and we'll take the domain of t to be all of x. This is one of those times where you can take the domain of the operator to be all of the ambient vector space. So certainly if f is a function from 0 to 1 into the complex plane, then x times f of x is also a well-defined function, and it's also a continuous function. And let's suppose that lambda is a point in the complex plane that's an eigenvalue of t with eigenvector f, and we're going to derive a contradiction. Something will go badly wrong if t is allowed to have an eigenvalue. So what does this mean? It means that tf is equal to lambda f. So that means that tf on x equals lambda f on x for every x in the interval 0 to 1, because tf and lambda f are functions. Functions are equal if and only if they're equal pointwise everywhere. And this means that x times f of x equals lambda times f of x for all x in 0 to 1. So this means that x minus lambda times f of x equals 0 for all x in 0 to 1. Okay, so this is what happens if I have tf equals lambda f. Let's consider some cases. Lambda is a complex number. So one of two things happens. Either lambda belongs to the interval of real numbers 0 to 1, or lambda doesn't. Let's suppose lambda doesn't. Suppose lambda is not in the interval 0 to 1. Either it's real and outside those intervals, or it has an imaginary part. Either way, we see that x minus lambda is non-zero for all x in the interval 0 to 1. And what does that mean? Well, x minus lambda times f of x equals 0, and x minus lambda is never 0, so f of x is equal to 0 for all x in 0 to 1. But then f can't be an eigenvector, because f is the 0 vector, and 0 vectors don't count as eigenvectors in the definition of an eigenvalue. The other possibility is that lambda is now a real number between 0 and 1. So again, we have something similar. X minus lambda is non-zero whenever x is greater than or equal to 0 and strictly less than lambda, and greater than lambda and strictly less than 1. So what does this mean? Again, I can use my relation x minus lambda times f of x equals 0 to show that f of x equals 0 for all x in the interval 0 to 1, except possibly this one point x equals lambda. But remember, we're working in a space of continuous functions. F is continuous on the interval 0 to 1, and so f of lambda is the limit as x goes to lambda of f of x, which has to be 0. So once again, f of x is equal to 0 for all x, and therefore f is not an eigenvector. So what did we do? We started with a seemingly innocuous linear operator tf at x is equal to x times f of x. We supposed that we had an eigenvalue. We considered two cases. The eigenvalue is not in the interval 0 to 1, or the eigenvalue is. And in both cases, we showed that any purported eigenvector would have to be identically 0, which is a contradiction to the definition of eigenvalue. So this linear operator has no eigenvalues. So later on, when we're talking about linear operators, like differential operators, on infinite dimensional vector spaces, it's going to be a little special, perhaps, for the operator to have eigenvalues. We cannot take the existence of eigenvalues for granted.